chemistry writes dot structures. We have to be able to do them. Now, dot structures are good for us to tell us what's bonded to what and how many, like if you have double bonds in there or all single bonds. So they're very helpful for us for representing molecules. However, one severe limitation that dot structures have, they don't give us any other information. Like they don't help us to know what the shape is. We have this thing called Vesper Theory for knowing what the shape is. You can't look at a dot structure and say anything about a shape, unless you know the Vesper Theory. I'll show you what I mean by that with one of our examples. Okay, so for number one, there's a 5-step process, by the way. When we do dot structures, the first thing that we do is we add up all the valence electrons from everything that's in the compound. Remember, we're going to have the formula of a compound, so the first thing we do is add the valence electrons. So you'll have the number of electrons, that's what we're aiming at. The next thing is, we have to start putting our structure together. You're going to take the least electronegative element and put that in the middle. The least electronegative element goes in the middle. So we know the trend for electronegativity. As we go down into the left, electronegativity goes down. So we want the farthest element down and left to go in the middle. Hydrogen, by the way, can't go in the middle. It's way over to the left. But you can't put hydrogen in the middle ever. It only makes one bond. So, yeah, it's never going to be a central atom. Number 3. Those outer atoms that attach to the central atom, I call them peripheral atoms. So we're going to take and we're going to attach all the peripheral atoms on the central atom with just single bonds. Those single bonds may change after we have to play with it, but at first put them on with single bonds. The next thing that we do is, this is where we have to account for the octet rule. This is a big time step. We have to get lone pairs around every side of every atom to make sure that all atoms have 8 electrons around. That's the whole purpose of bonding, is to get 8 electrons around all atoms. All right, the first 4 steps are quick hitters, and then we get to step number 5, more wordy. So here's what, now we have to put it all together. If your structure has too many electrons, like let's say that you make up your structure and it's got 30 electrons, but you can only have 28. You got too many. So what you want to do is you make double bonds and triple bonds if you need to, and it tells you after that what to do. I'll give you some examples. Oh, thank you. Yeah, you may encounter times when you actually don't have enough electrons. Maybe you've got 30 in your structure, but you need 32. So you got to put 2 more on there somewhere. Everybody's already got 8 electrons. You'll have to add the 2 more electrons to the central atom always. I'll have an example of that for you too. Okay, we all good? So now for just about the entire rest of the hour, we'll just do some examples of making dot structures. If you can't see the wall periodic table, then have one out so that you can look at it. We'll need it. The first example I have for you is selenium difluoride, SeF2. So step number 1, you're going to see that I'll do the same steps every time. I want to make this very systematic. And when we kind of catch on to the system, then there's no big surprises. There's no difficult ones. There's no especially easy ones. They all just are done the same way. As shown. Se, we find Se on the periodic table. It's in the oxygen family with 6 valence electrons. So I'll just account for them like this. There's 2 fluorides. Each fluoride has, not fluorides, fluorine has 7 valence electrons, so 2 times 7. So 6 plus 2 times 7 gives us 20. So we're going to need a structure to represent SeF2 that shows 20 electrons. By the way, if you learned a different way of doing dot structures in Chem 1, maybe you had a teacher that didn't do it quite this way, I am going to encourage you to try to catch on to this, not because it's my way or the highway, that's not it at all. I think that as dot structures become more complex, and molecules become more complex, it's good to do the dot structures this way. So just an encouragement to you, and feel free to seek me out if you have any questions about this differing from what you've learned before. Now, step number 2 is we're going to determine which one is the central atom and put that one in the middle, or down first. The least electronegative element is going to be the one farthest down and left. Fluorine is the highest electronegativity element on the whole periodic table. So that's never going to go in the middle. So we're down to one choice. Selenium will go in the middle. Now, step number 3, add the fluorines to it with single bonds for right now, and we'll see if we need to change those. Step 4, add lone pairs to get everybody 8 electrons around. Okay? Just add those pairs. If you had a Chem 1 teacher to use lines instead of pairs of dots, use the lines, whatever you like. I don't care. They say the same thing. All right, so now every atom in this structure has 8 electrons around it. By the way, watch out for hydrogen. Don't ever put hydrogen or lone pairs on hydrogen because they can only have 2 electrons total. So the bond takes care of hydrogen. Once you have your lone pairs put on to give everybody 8 electrons, now we're down to step 5 already. Step 5 is count the total number of electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. If that number that's represented in the drawing is equal to the number that we came up with in step number 1, then we're done. That is the dot structure. We don't need any double bonds or anything. So SeF2 just looks like that. Now, a couple minutes ago, I mentioned that dot structures have a drawback. They don't help us to know what the shape of a molecule is. When you look at this dot structure, does it make you think that the structure is linear? The actual shape is linear? It looks like it's a linear molecule. However, it's not linear. It's not. Does anybody know what the shape is? Do you remember from doing shapes? Don't be sad if you don't. Rishi? It is bent. Yes, it's bent. because that selenium has the two lone pairs on it. They kind of spread out and push down on the bonding pairs. That makes it better. Yeah. So let me just warn you. Don't be fooled by what a dot structure looks like into thinking that's what its shape is. Usually it's not. Usually it's not. So just be aware of that. We'll work on it. We're going to talk about shapes tomorrow. Okay, so that's done. The number of electrons shown there equals the number there. Everybody's got 8 electrons. We're good. The next one is CO2, carbon dioxide. Count the number of electrons first. Carbon has 4. Oxygen has 6, and there's 2 oxygens. So we got 16 electrons. Put the carbon in the middle. That one's less electronegative than oxygen. And then connect the oxygens with a single bond. That takes us through step 3. Step 4, add your lone pairs. There they are. Everybody now has 8 electrons. We feel like we're good to go, but there's that last step. Check to make sure that the number of electrons in here equals that number. In this case, it doesn't. Count them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I got 20 electrons shown, but this thing should only have 16. You see that? So we have to get rid of 4 electrons. What do we do to get rid of 4 electrons? That's what I was talking about now down here, number 5. If you have too many electrons, yeah, we do. Make double or triple bonds on adjacent atoms. What does adjacent mean? Adjacent. Next to, right. Already bonded to, that's adjacent. Erasing lone pairs from each. I'll show you what I mean by that. And you probably already have known this, and you're just being polite and watching as I do. You can take the carbon and the oxygen on the left are already bonded to each other. These are adjacent atoms. What we would do to get rid of some of the electrons is, oh boy, that erasing circle is huge. Erase the lone pair from that oxygen and the lone pair from that carbon. And instead of each of those having their own lone pair, they'll share one pair. So both the carbon and the oxygen still feel both of those electrons, both those pairs of electrons. They now are sharing, which has cut us down by 2 electrons. So we had to get rid of 4, making a double bond there, got rid of 2. So we erased 4, but then added 2 back in. That's a net change of -2. So we need to get rid of 2 more electrons. Now, you have a choice. You could either erase those 2 and make a 3rd bond between those, or you could make a double bond over here on the right. Now, with just pure dot structures, it doesn't matter. You can definitely make a triple there and a single there, and it's fine. However, the more correct structure has a double bond there and a double bond there. There's something called formal charge that's going to dictate that. We'll do formal charge on Monday next week. So, I'm going to go ahead and erase the lone pair that was underneath the carbon, the lone pair that was there, and fill in another bond there. So still, both the carbon and the 2 oxygens all have 8 electrons around them, except now we've cut down the total number of electrons by 4, and that would be the dot structure of CO2. That good? All right. Would you try this one? The perchlorate ion, ClO4 with a -1. So we have a polyatomic ion in this case. The polyatomics are always held together with covalent bonds, though, so it's no big deal.